Hello everyone. In this lecture, we will consider a topic which is very important in analyzing the performance of an algorithm, asymptotic notations. Myself, Dr. Sminu Isuddin, Associate Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. This is the overview of today's lecture. We will first briefly see what are the different factors which influence in analyzing the performance of an algorithm. Then we'll see asymptotic notations, various asymptotic notations, big O, big omega and big theta, and we'll do an exercise. We know that the two factors which influence the performance of an algorithm is its space complexity and time complexity. And in previous lectures on data structure, you already seen how to calculate the step count value of an algorithm and later to represent it as a function. So in today's lecture, we will see how to calculate the asymptotic value from this step count value of the function. So, what is asymptotic notations, or why you need asymptotic notations? As time complexity, we are using functions in algorithm. That's the reason why we are using these notations. So these notations are actually used to represent simple form of a function or to show the class of a function. So they are actually used to represent this function in simple form so that we can easily get the idea. That is why we are using these notations. Because it is always not possible to represent a lengthy function. So we need a simple method to represent time complexity. So that is why we are using these asymptotic notations. Now before we begin, let us quickly refresh the comparison between the function, or let us try to write this function in increasing order of their value. So always remember, given the increasing order value given in the slide, this is the order 1 lesser than log n, lesser than root n, lesser than n log n, again which is lesser than n square, n cube, 2 raised to etc 2 raised to n, 3 raised to n, etc n raised to n. That's how generally a function grows. The most common asymptotic notations are big O, which represent the upper bound of a function, big omega, which represent the lower bound of a function, and big theta, which represent the average bound of a function. Any function can be represented as upper, lower, or average bound. But since big O represent the upper bound of the function, generally big O notations are used to represent the worst case complexity of an algorithm, but not necessarily a worst case complexity can be represented using any of these three forms, but generally big O represent the worst case complexity and omega represent the best case and theta represent the average case complexity of an algorithm. Now, as I said, any function can be represented as a upper, lower, or a average bound. But since theta represent the average case, it is more useful because it gives more accurate picture of your function. So that is why theta is considered to be most important. Okay, then why you need big O or big omega? You need big O and big omega because in many of the cases it's not possible to specify the exact place of a function. So if it is not possible to specify the exact place of a function, then on a safer side we can go for either of these upper or a lower bound. Okay, so to understand more about these asymptotic notation, let us start them one by one. Now in the next slide we will see how can you represent a big O notation, or how can you represent a function as its big O value.
Assume that the complexity of a function can be represented as, say, f of n equals say some function 3n plus 2. That is, the complexity or the step count value we calculated represented in terms of a function as f of n equals 3n plus 2. Now, In order to find the big O value of this function fn, I need to find another function g of n. I need to find another function g of n and a constant, positive constant c, such that c into g of n, if it is always greater than or equal to your function f of n. That is, I can represent my function f of n as the value of f of n is always lesser than or equal to c into g of n, or I can identify a function gn such that c into g of n is always greater than my function f of n. Then I can represent my function f of n as big O of gn. That is, our condition is, you have to identify a function c into, you have to identify a constant, positive constant c into g of n such that it is always greater than or equal to the function fn, and of course the function is greater than or equal to 0. Then I can represent my function f of n as O of gn. Okay. Now in order to understand this, let us draw a plot. Okay. So suppose I am going to draw a graph where on the y-axis I am drawing time and in x-axis it is n. Now suppose the function fn I can represent like this. This is my function f of n. Okay. Now suppose I draw c into g of n into this. Now suppose this is c into g of n. That is, our aim is to find a function which is lying above f of n. Now when you observe this function, we can see that for larger values of n, that is exactly from this point onwards, my function c into g of n is lying above the function f of n. Right? Now this particular point, we'll call it, suppose I name it as n0, this is called the break-even point. Or asymptotic notation actually satisfy for larger values of n. Now, in using asymptotic notation, what we are trying to find is how the value of the function behaves for larger values of n. Right? Now, when you observe, we can find that from this point onwards, the value c into g of n is larger than f of n. If this is true, so the condition, again I am writing, it is f0 lesser than or equal to f of n lesser than or equal to c into g of n. Therefore, there exists a positive constant c and another positive constant n0. Then I can write f of n as big O, asymptotic big O of g of n.
On summarizing, we found that big O represents the upper bound of a function, and it is used when we cannot specify the exact place of a function. Now we can define big O of a function f of n as f of n can be written as big O of g of n provided there exists positive constant c and n0 such that 0 lesser than or equal to fn lesser than or equal to c into g of n for all n greater than or equal to 0. Now in the next slide we will see how can you calculate the big omega value or lower bound of a function.
Now let us find the asymptotic big omega value. Okay. Now again let us consider a function fn. Let us take the same function f of n equals say 3n plus 2. Now your aim is to find the big omega value, which means the lower bound of your function. Okay. So again consider a positive constant c and another positive constant n0. So suppose your function f of n can be written as, suppose you are able to identify a function gn such that c into gn, where c being this positive constant, suppose c into gn, if it is always lesser than or equal to your function, okay, so of course then I can write, of course this is a positive function, so 0 lesser than or equal to c into gn, then I can write f of n as omega of gn. So your function fn, suppose you are able to identify another function gn such that if there exists a positive constant c, such that c into gn, if it is always lesser than or equal to the function fn, then I can write f of n as omega of gn. Okay. Now let us draw the plot. Maybe in x-axis I can represent n, and in y-axis say time t. Suppose this is your function fn. Now your aim is to identify c into gn. Suppose c into gn, this is c into gn. That is, say this being your break-even point n0. This is your break-even point n0. So a function fn always lie above c into gn from this point onwards, right? Now if you are able to identify that, then I can write my function f of n as omega of g of n, or this represent the lower bound of your function.
So we found that omega represents the lower bound of a function. Now we can formally define omega as f of n can be written as omega of g of n provided there exists positive constant c and n0 such that 0 lesser than or equal to c into gn lesser than or equal to fn for all values of n greater than or equal to n0. Now in the next slide we will try to find out how can you calculate the average bound or a theta value of a function.
Now we'll see the average bound or theta value, or we'll try to find big theta. Okay. Now let us take the same function fn. Say fn equal 3n plus 2. Okay. Now my aim is to find the average bound of this. Actually, theta notation is considered to be the most useful because it will give you an exact picture of your function, right? So here we need to find three positive constants, c1, c2, and your break-even point n0. Okay. Now your aim is to find a function gn such that c1 into gn, that is lesser than or equal to your function fn, and c2 into gn is greater than your function fn. Then of course it is a positive function, so 0 lesser than or equal to. Then I can write f of n as theta of g of n. Okay. So you identify three positive constants c1, c2 and n0 such that c1 into gn is lesser than or equal to a function and c2 into gn is greater than or equal to a function. Then you can write f of n as theta of gn. Now again when you try to move the plot with a y-axis you represent time and in x-axis you represent n. Then if this is your function f of n, then we have to identify, we have to draw c1 gn and c2 gn. Suppose this represent your c2 gn which lies above this, and maybe this represent your c1 gn which lies below n. Then this particular point can be my break-even point. Okay. So your aim is to so you are able to identify two positive constants c1 and c2 such that c1 gn is below your function and c2 gn is above your function. Then you can write f of n as theta of gn, and this is your break-even point.
and hence theta represents the average bound of a function. Since it represents the average case, it is considered to be more useful because it gives you more accurate picture of your function. Now we can formally define theta as f of n can be written as theta of g of n provided there exists positive constants c1, c2 and n0 such that 0 lesser than or equal to c1 gn lesser than or equal to fn lesser than or equal to c2 gn for all n greater than or equal to n0. Now in the coming slides we will try to work out an example where you'll try to calculate the big O, big omega and big theta value of a function.
Now we'll see how can you find the asymptotic big O value of a function. Let us consider the same function f of n equals say 3n plus 2. Our aim is to find the big O value of this. So what is the equation? That is f of n can be written as O of g of n provided there exists a positive constant c such that c into gn is greater than or equal to fn provided it is a positive function, right? So our aim f of n can be written as, should be able to write it as something into gn. Okay, so here our function is 3n plus 2. So our aim is to find a c into gn such that 3n plus 2 is lesser than or equal to that. How can you do that? Now there are different ways by which, for example, suppose I take this 3n. I want to have something in the right hand side such that the right hand side is greater than or equal to my left hand side. Okay. Now the simplest way to do that is just replace this by, see here I am having two terms. There is a 3n term and there is a 2 term, right? So I am going to write it as 3n plus, let me replace this by another n into n, 2n. Okay, so what I'm getting here 3n plus 2 is lesser than or equal to 5. Is it true? Yeah. For all values of n, maybe for all values of n greater than or equal to 1, this condition is true, right? Maybe you can check. For example, if the value of n is 1, here I'll have 3 into 1, 3 plus 2, 5, and right hand side is also 5 into 1, 5. Suppose I take the value of n as 2, then it is 6 plus 2, 8. 8 is lesser than or equal to 10. So it is true for all values of n greater than or equal to 1. Right? Now if I can do that, then what is the advantage? This is my fn. Fn I can write it as, I can take this as my c and I can assume this one as my gn. This is my gn and this is my c. Okay, so which means what? F of n can be written as, what is the condition? F of n can be written as, if that is the case, f of n can be written as O of n, provided there exists a positive constant c whose value is 5 and it is true from all values of n greater than or equal to 1, or a break-even point n0 is 1. Okay, now if this is the case, when I find, is it if I consider some other value, say instead of this 3n plus 2, my 3n plus 2, instead of this, if I write some other value, say if I'm writing it as 6n, is it true? Yeah, it's true. If I consider, instead of 6, if I consider 7, is it true? Then also true. If I consider 10, is it true? Yeah. So in that case, you will have different values of C and N0 combination. Right? So what we concluded is, I am going to write my function f of n, which is equal to 3n plus 2. I can write my 3n plus 2 as O of n. Okay. Now, if that is a case, then suppose instead of this function 3n plus 2, suppose I'm going to write this instead of n, if I'm writing it as n square. Now, will that be true? That is, if I'm going to write it as 3n square plus 2n square, which means, is 3n plus 2 greater than or equal to 5n square? Yeah, true. So in that case, what happens? My function, this is my C and this is my Gn. Okay, so now what we concluded? We concluded that my Fn can be written as O of n square. Is it true? That is true. That is also true. So my function can be written as O of n, or my function can be written as O of n square. That is also true. So can I write it as f of n? Is it true if I write O of n cube? That is also true. Right? Now look at this relation. If I consider any value, that is your function f of n, function 3n plus 2 is actually mapped to this one. So if I consider any value which is greater than this, it will be true. If I can consider any value in this bound, it will be true. Okay, so I can write either it as f of n equal to n. I can write it as f of n equal to O of n square, that is O of n. I can write it as O of n square. I can write it as O of n cube. All are true. Okay, then what is the advantage? So definitely there will be confusion, but the apt method is, or even though if I write it as O of n square, it is not wrong. It is not of good use for us. So your aim is to find a function which is little more closer. Okay, so that is why if you can write it as O of n, then you won't consider these. So the best method is conclude it as O f of n equals O of n. Even though these three are all are true, you can write anything in this range. Suppose your function is n, you can consider any value. 3n plus 2 can be written as O of n log n, can be written as O of n square, can be written as O of n cube. Any value in this side, it is true. That is why it is called the upper bound. Okay. Now, when you try to represent as the plot, now how our plot look like? This is a plot. This is 0. This is n. This is t. Now, suppose this is your function 3n plus 2. I can find. Now, here, found the function. This is my 3, 5, n. Or this is nothing but c into gn, and this is my f of n. It is true for all value from 1 onwards. This is n equal to 1. Now we'll see how can you find the big omega value of the function. So let us consider the same function f of n equals 3n plus 2. Now our aim is to find the big omega value or the lower bound of the function. Okay. Now for that, what's the relation? F of n and omega, what is the relation? C into gn should be lesser than or equal to a function fn. Or 3n plus 2, if you have the function 3n plus 2, I should be able to write, or I should be able to find a function gn and a constant c such that the value of that should be lesser than or equal to 3n plus 2. The simplest method is replace this by 1n. So 1n, I know it is lesser than or equal to c into 3n plus 2. Okay. So here, if I write like this will become my c and this will become my gn. Or that is definitely it is lesser than or equal to 3n plus 2. Or I can write it as f of n equals omega of gn, which is n, which is true. Okay. So f of n, I can write it as omega of n. Now, if this is true, then can I replace this by, instead of n, can I replace it by log n? Yeah, that is true. Or I can write f of n as omega of log n. That is true. Okay, I can, why is it true? Because this function 3 of n, it is actually mapped to this. So you can replace it by any value in the left hand side. That will be true. But definitely I can't write f of n equals omega of n log n. That will be false. So I can replace it by any value in this left side, but I can't replace it on the right side. Okay, but even though if I write f of n equal to omega n, I can write it as f of n equal to omega log n, can write it as, or or even I can write it as f of n equal to omega of 1. All are correct. But the apt one or more appropriate one is the one which is more closer, or that is f of n equal to omega of n. Right? So when if I try to draw the plot, this is 0, n and t. Suppose it's the function f of n. It is true for all, that is f of n, I can write it as omega of n for all values. This is true for all value of n greater than, or actually it is true from 0 onwards. Okay, so what does it mean? The function c into g of n, which will lie beneath this. So this is my c into g of n. This is nothing but my function 3n plus 2, and this is the function n. Okay, so I concluded I can write f of n as omega of n, provided there exists a positive constant c equal to 1, and which is true from all value of n greater than or equal to 0. So that is big omega value. Now we'll try to find the asymptotic type bound at theta value of the function. So let us consider the same function f of n equals 3n plus 2. Now what is theta? Now to find theta, you need to identify three positive constants c1, c2 and n0 such that if there exists a function gn, then c1 into gn is lesser than or equal to the function fn, which is again lesser than or equal to c2 into gn. Of course, it is a positive function. So if you are able to identify positive constant c1 and c2 like this, then you will be able to write your function f of n as theta of gn. Now we already calculated this for big O value, and so we can write 3n plus 2, which we already calculated. Upper bound we calculated it as 5n, and lower bound we calculated it as 1 into n. Or your function f of n can be written as, now what, f of n can be written as theta of n. Why? Because here 5 is my c2 and say 1 is my c1, where the function is gn. Okay, the gn function here it is n. So for the function gn to be equal to n, where c1 equal to 1 and c2 equal to 5n, I can write this. So my function f of n can be written as theta of n. F of n can be written as theta of n. Okay, now remember when we discuss big O value, I said this function 3n plus 2, this function's big O value 3n plus 2, the function 3n plus 2, big O value, it can be written as O of n. It can be written as O of n square also. It can be written as O of n cube. It can be written any value in the upper range, the big O value, right? Similarly, when we calculated the lower bound 3n plus 2, the omega value, we found it as omega of n. But at the same time, it is not wrong to write it as omega of log n, right? Or I can choose any value in this lower region, omega value. So here lies my omega and here lies my big O, right? Now, but when we consider here, suppose, let us say that 3n plus 2, suppose I am writing it as O of n square. O of n square, that is I can write it as 5 n square, right? So this is true. But I can't write, when I look at the left hand side, I can't write it as less 1 n square lesser than 3n plus 2, which means it is wrong here. Or I am supposed to, similarly, when I consider the omega value, I said omega can be n, omega can be log n, omega can be even 1. That is also possible. But now, so when I consider this function 3n plus 2, it is not wrong to represent the function as 1 into log n. But I can't write it as which is lesser than or equal to 5 into log n. So this is wrong. Here it is wrong. So which means that you are supposed to find, or you should fix the value of n, of the upper bound, tight bound or a theta value as n itself, or you should write it as f of n equal to theta of n. F of n equal to theta of n, or that represent the tight bound. So that is why we are considering theta to be the best accurate case, because it will give you more accurate value. You can't write, now if I take n square value of gn, if I take value of gn as n square, this half will be okay, but it will fail in the left hand side. If I take the value of gn as log n, this half will be okay, but it will fail in the right hand side. Or you are forced to stick on to the value of gn as n, right? Now when we try to draw the plot, we can see that, say this be my plot, where this is here I can have t and this is n. Suppose this is the function 3n plus 2. Okay, now here lies your lower bound, which is 1n, and lies the upper bound, which is 5n, and this point will be a given point, or n0 equal to 1. Or this is true only for value of gn equal to n. Or I can write theta of my function f of n as theta of n, provided there exists positive constant c1 equal to 1, c2 equal to 5, and for an n0 equal to 1. So that is theta notation.
In this lecture, we saw how to represent the time complexity of a function in terms of asymptotic notations. We tried to calculate the upper, lower and average bound of a function in terms of big O, big omega and big theta value respectively. These are my references. Thank you.